Hi guys, my name is Michael Vincent Udousoro, a master's student in Udousoro University in data science. I'm here to talk about this project on human locomotion activities based on time series data. The objective of this research was to utilize machine learning and deep learning methods to classify human locomotion activities based on time series data from the UCI-HAR dataset. This task is critical for applications in healthcare, fall detection, and smart home systems. In this research project, we compared traditional machine learning algorithms like logistic regression, random forest, and support vector machines (SVM) with advanced deep learning algorithms. Also, specifically the recurrent neural networks and also the LSTM, which is a long short-term memory, to assess their performance in recognition human activities. Also, in this project, human activity recognition (HAR) is a pivotal in healthcare and security monitoring, but present challenges like sensor noise, proper placement, and overlapping activities are being hindered in this research. This study aims to improve recognition accuracy through robust algorithm and hyperparameter tuning. So, in this research, we are going to talk about the data preparation, how we start about this. So from here, for the data set, we got our data set from, we use the UCI HAR dataset, a benchmark dataset comprising time series data captured by smartphone, accelerometers, and gyroscopes. Also, we will talk about the data set includes activities like walking, running, standing, making it ideal for testing classification models. So now we will have to talk about the pre-processing of this data set. So the data was filtered and normalized to remove noise and scale the features using techniques like scalar fit. This step include uniformity in the input data. As we have seen here, training the data with the X and Y, and then we move about to normalizing the features of the dataset. And also, the dataset was split into training, validation, and testing sets for robust performance evaluation. And we have to go down to our machine learning models that we used in this research purpose, which is now we define our models: logistic regression, random forest, support vector machine. We are going to talk about this one by one, in which this is our regression logistics. So now we talk about our regression logistics or logistic regression model. So this predictive model was used as a baseline due to its simplicity and efficiency. It models the relationship between a dependent variable and independent variables. So that is what the logistic regression model does. And here we can see our logistic confusion matrix and our input and the results that we've got. We move down to our random forest model that we use here. So for the random forest, an ensemble method builds multiple decision trees and averages their output for improved accuracy. It's effective in handling noise and irrelevant features. Here, that is what our random forest model does. So now moving on to our support vector machine model that we use here for classification report. For our SVM, it separates data points using hyperlink and is particularly effective for classification tasks with non-linear boundaries when using kernels. Here we can see how we use the support vector machine with the accuracy, which we got here, and classification, precision, recall, F1 score, and support. And for our confusion matrix where we got for our support vector machine, here it is. So also comparison with evaluation metrics such as precision, recall, and F measure. So we have to move down to these are the codes that we use to derive to get all these results. And moving down to this our table logistic regression, random forest, and support vector, we can see here that the logistic regression achieved 95.5% accuracy but struggle with nonlinear relationship. And also in this table, we can also see the random forest perform well with 92.4 accuracy but showed overfitting tendencies. And also the SVM achieved 95.18 accuracy with nonlinear kernel demonstrating robust and also demonstrating robustness. So these are what we've got using the machine learning model in doing the classification and testing accuracies and then comparing it with the model we use. So we have to go down to our deep learning algorithm, which we use machine learning and deep learning models in this. So here, talking about the uh, importing our data and pre-processing labeling. So we have to talk about the RNN with hyperparameters for tuning. So for the RNN was implemented to leverage sequential patterns in time series data. However, it faces challenges like vanishing, in which this is the challenge about the vanishing that we've encountered when using the RNN method for testing and training of the model. So moving down to our LSTM, LSTM extends RNN with gating mechanisms to return long-term dependencies, addressing the limitations of our RNN. So here we have seen how the LSTM extends RNN with gating mechanism with our code and training LSTM with units and also activation, reload, batch size, and epoch. So these are what we've got when doing it. So for now, moving on to model training, hyperparameter tuning in the training machine learning models. So machine learning models were trained using scikit-learn with default and optimized parameters. Perform Performance was evaluated using metrics like accuracy, precision, recall, and F1, where we got in this our from our table here precision, recall, F1 model. And also training the deep learning models for RNN and LSTM, TensorFlow was used. Data was reshaped into 3D format for compatibility and also with the models to be compatible with the models that we use. Hyperparameters like the number unit where we got our hyperparameter tunings like the number unit, activation functions, reload, tanch, batch size, and epoch were also introduced using the grid search. Example for LSTM, if we use code this in Python, that is what we're going to have, and then the accuracy will be performed. So For the performance evaluation metrics used, so this was our LSTM with hyperparameter tuned, where we train our model and then check it out, and the activation, reload, bash, and turns and epoch. So for accuracy, a performance, so this is where we plot our RNN versus the LSTM accuracy over epoch. Accuracy was the primary metric, complemented by precision, recall, and F1 score to evaluate class size performance. Confusion metrics provided such insights into misclassifications, especially for overlapping activities like sitting and laying. That is what we've got when we compare this. So for the result of our machine learning, where I had already talked about how we achieved the 95.5 accuracy in logistic regression, and also we got random forest perform well with 92, and also SVM achieved with 95%. So moving down to, let's talk about the results that we got for our deep learning models. So the result we got for our deep learning models, we've seen that using the RNN, we achieved 94% accuracy with good sequential pattern recognition, but validation instability. LSTM LSTM outperformed all other models with 95% accuracy. It gives us 95% accuracy and 95% accuracy, excelling in generalization and long-term dependencies detention retention. So here we can see from our code and all our plotting to check about our loss and epoch. So that is what we've been able to achieve in this project. Using this to predicting this using the RNN models. So we now use the comparative analysis where we compare RNN versus LSTM to check over the accuracy, and also plotting the plotting the visual representation of it. So for the comparative analysis, deep learning models, RNN and LSTM outperform traditional machine models due to their ability to capture sequential patterns. And we've seen the patterns here, how it has been able to capture sequential patterns among the two models. Also, among machine learning models, logistic regression and SVM perform similarly, while random forest shows slight overfitting. So that is why in this project, deep learning models was mostly acceptable with this project because of its performances. For the accuracy, the deep learning models achieve higher training accuracy compared to traditional models, but LSTM maintain better validation in accuracy. So we're moving down to about for our confusion metrics. Here we talk about the challenges we faced, of the challenges for the hyperparameter tuning, finding the best parameter for random forest number of trees, SVM, kernel, C, gamma, and deep learning models like number of layers, learning rate was time consuming. These were the challenges we faced in this research project. But for moving down to our computational resources, training deep learning models like LSTM required more computational power compared to traditional methods. That is what this project we've been able to derive and then found all this while working in this project. So we're talking about the overfitting. The RNN and random forest model showed signs of overfitting, especially on the training set. Improve that is was some of the challenges we face when were dealing with overfitting, and also improvement and future work. Here are some of the ways the models can be improved, and also here this was the accuracy, the model comparison with accuracy, precision, and F1 score, where we find our logistic regression, random forest, SVM, best RNN, and best LSTM. Here we can see how the models gives us different answers, and also the best fit and the best was picked here, where we marked our best RNN and our best LSTM when dealing with this model, because the deep learning models achieved higher training accuracy compared to these traditional logistic regression, random forest, and LSVM. For the last, LSTM consistently showed the lowest training and validation of this validation like validation loss, indicating effective learning and better generalization in this project. So, improving in this future work, here are some ways to improve the models. Regularization. So if we are working about with regularization, apply dropout of L2 regularization to deep learning models to reduce overfitting. Also talking about the data argumentation, increasing increasing the dataset size using argumentation techniques, and also advanced architectures. Explore GRU gated recurrent unit or transformer models for deep learning for deep learning, and also using tools like Bayesian optimization for faster high parameter tuning in this hyperparameter optimization. In conclusion, the key findings in this research was logistic regression provided a good baseline but struggled with non-linear dependencies. Random forest and SVM performed well for tabular data but fell short capturing sequential relationships and other lots more. RNN and LSTM excel due to the ability to model time series data, with LSTM outperforming all models in terms of validation, accuracy, and loss. Also, a further experiment with advanced architectures like transformers or hybrid models combining traditional machine learning and deep learning could yield better results. Thank you.